Okay, so welcome everyone to today's lecture. So today we will continue with yesterday's lecture where we talk about the formula for the inverse of a matrix. So remember, suppose from yesterday, suppose A is invertible. So if A is invertible, then we can find the inverse of A inverse by using the formula 1 over determinant of A multiplied by the aggregate of A. Okay, so we talked about this theorem yesterday. And today, first of all, we will talk about the Cramer's rule, which we will use this formula in trying to solve the system of linear equation in the form of AX equals B. So any system of linear equation can be rewritten in the matrix form AX equals B. And in this case, we are considering all the situation where the matrix A is invertible. Okay, so let me remind you, this Cramer's rule only applies to the system where the coefficient matrix is invertible only. If the coefficient matrix is not invertible, then you cannot use this Cramer rule. Okay, so remember, if the coefficient matrix A is invertible, in order to find the variable x, all you need to do is to multiply both sides with the inverse of A on the left. Okay, so equivalently, this system is equivalent to saying that x is equal to A inverse and then multiply that with column vector B. Right, and so far we have learned the formula for the matrix A inverse. So I'm going to use this formula over here. I'm going to plug that into this formula. So you should have x is now equivalent to 1 over determinant of A. And then we have matrix aggregate of A multiplied with matrix B. So remember, x here is a column vector. Okay, x here is a column vector. So suppose if I want to find a specific entry in this matrix, in this column vector, suppose I want to know the value of the entry xi, then I need to find the entry xi in this matrix, right? This 1 over determinant of A is already a number. So we only need to look for the I entry of this column vector over here. So xi in this case should be equals to 1 over determinant of A multiply the I entry of this matrix. I entry of this matrix. Okay. So we have two matrices and they are multiplying with each other. So remember this is a square matrix. The aggregate of A is a square matrix and B is a column vector, right? So because I am trying to find the I elements of this multiplication, I'm going to use the I row from the first matrix and I'm going to multiply that with the column of the vector B. Okay, so this is equivalent to 1 over determinant of A multiply the sum. Okay, so I am using the I row of this first matrix. So it should be aggregate A, Ij. Right, I stands for the row and J is the column. And then I'm going to multiply this with the column of the matrix B. So I multiply this with Bj. So J runs from 1 to n. Okay, suppose that the size of the square matrix is n by n. Okay. So when people are using this formula, they realize that this sum over here, it looks like the Laplace expansion. It looks like we are using the Laplace expansion in trying to find a determinant of some special matrix, right? And they realize that this is actually equal to the determinant of a special matrix that they would call in this case A1. Okay, they realize that this sum over here is actually equals to the determinant of a special matrix AI, where AI is the matrix A plus I guess okay, so where AI is the matrix obtained by replacing the I column of matrix A with B. Okay, so they realize that that sum over there is actually the determinant of matrix A, matrix AI, where AI is the matrix that we can obtain by replacing the I column of the matrix A with the vector B. And that is actually what is called a Cramer's rule. Okay, that is actually what we would call a Cramer's rule. So as you can see, first of all, let me remind you, this rule is only applied to the case where the coefficient matrix is invertible. And by using this rule, you can actually find a specific entry of the variable vector without having to solve all the vectors, right? For example, if you are only interested in some specific entry in the variable vector, then you can use this formula here, just to try to solve for that entry only, okay? So let's try to use this rule in an example, okay? Example. Let's try to solve this. Okay, so this is the coefficient matrix. We got 1 to 1. We got 3 to 1. We got 2, -1, and the variable vector, we got x, y, and z. And for the constant vector, we have 1, 2, 3. Okay, so this is the matrix A. This is the variable matrix X. And this is the constant matrix B. And here I am only interested in the variable X only. Okay, so even though we haven't checked that A is invertible, so in order to check if A is invertible or not, you only need to find the determinant of A. So first of all, we will do that. Okay, let's try to calculate the determinant of A. So the determinant of A. Okay, so here, because A is a 3x3 matrix, I'm going to use the low path extension right away for that, using any type of row operation. So I am expanding along the first row. Okay, so we should have 1 multiplied by determinant of 2, 1, -1, 1, minus 2 multiplied the determinant of 3, 1, 2, 1, plus 1 multiplied the determinant of 3, 2, oh, sorry, 3, 2, 2, -2. Okay, so this is 5. Minus 2 multiplied by 1 plus 1 multiplied -13. Right, that is -9, -4. So we got 5 minus 2 is 3, 3 minus 13, we got -10. Oh, I'm sorry, did I make any mistake? Oh, okay, anyway, let's stick to this example. It's okay. So as you can see here, the determinant of A is -10, which is non-zero. So it guarantees that A is invertible. And since A is invertible, we can use this Cramer's rule over here. Okay. And because I am only interested in finding X, so in order to find X according to this formula over here, you only need to find the determinant of the matrix AI. So in this case, it should be A1. Okay, so I am trying to find the determinant of A1. So what is A1? A1 is actually the matrix A, but you are replacing the first column with a constant factor. So this is the first column, 1, 3, 2. We are going to replace that with 1, 2, 3. Okay, and we keep the other two columns. So 2, 2, negative 3. And 1, 1, 1. And once again, because this is still a 3 by 3 matrix, I'm going to use a low path expansion, expanding along the first row. So we should have 1 multiplied determinant 2, 1, negative 3, 1, minus 2 multiplied determinant of 2, 1, 3, 1, and plus 1 multiplied determinant of 2, 2, 3, negative 3. Okay, so we have 1 multiplied by 2 plus 3, which is 5, minus 2 multiplied by 3 minus 2 minus 3, which is negative 1, and then plus 1 multiplied by negative 6 minus 6, which is negative 12. So we got 5 plus 2 is 7, 7 minus 12 is negative 5. So according to the Cramer's rule, X is actually equal to the determinant of A1 divided by the determinant of A. So we should have negative 5 and divide that by negative 10. So the answer is 1/2. Okay. Yeah, so this is called the Cramer's rule. So do you have any question? Yeah, if you are interested in other variable like Y and Z, you can continue using this one, right? So if you're trying to find Y, it will be determinant of A2 over determinant of A. If you want to solve for Z, it should be determinant of A3 over determinant of A, and so on and so on. So I'm just going to use X as an example over here. Okay, so that is the Cramer's rule. Let's talk about the next part of today's lecture, which is the polynomial interpolation. Okay, let's talk about this. Interpolation. Polynomial. Okay. So in many fields, when you are trying to investigate the relationship of two objects, normally people would trying to collect data about those objects, okay? And the data will be represented in a plane as a dot with two coordinates. The X just like the normal point with X coordinate and Y coordinate. And after they have collecting some data about these objects, there would be some data represented on the plane. And these data will represent the relationship between these objects in some specific situation. And now people are trying to find a model to represent the relationship of these two objects in general. So people would need to find a function that will fit all of the data. Okay, people would need to find a function that would fit all the data. And the wisest choice now is a polynomial, because polynomial is a function that is the easiest way to work with. So the process that given some data point, you are trying to find a polynomial that is fit to all the data point is called polynomial interpolation. Okay, that is basically what is polynomial interpolation. Okay, so in this section of the lecture, we will have one theorem. Let's start by saying this theorem over here. Okay, so given n data point, so suppose all the data points are in the form of x1, y1, up to xn, yn. Okay, where the x coordinate are distinct, okay, with distinct value of x. So if that is the case, then there is a unique polynomial. There is a unique polynomial. So we would call this polynomial Px R0, R1x up into Rn minus 1 x to the power of n minus 1. Such that Pxi is equal to yi for I equals 1 to up to n. And Px is called the interpolating polynomial for the data point. The okay. So as you can see, if you have n data points, then you should be able to find a unique polynomial where the degree is n minus 1 at maximum. Okay, sometimes this coefficient Rn minus 1 becomes 0. So the degree of this polynomial should be less than n minus 1. So remember that the degree of the polynomial, the interpolating polynomial, is always n minus 1 at maximum. Okay. So let's try to apply this theorem in an example here. Okay, so for example, given the data. Okay, so here I have 4 data points. We got 0, 1. We got 1, 2. We got 3, 22, and 5, 66. 3, 22, and 5. So we are having 4 data points. And all we need to do is to find the Px interpolating polynomial. Okay, so because we are giving 4 data points, so the degree of the Px should be less or equal to 3. Here n is 4, so n minus 1 is 3. So let's try to call out the form of the Px. So suppose Px is in the form of R0 plus R1x plus R2x squared plus R3x3. So this polynomial here has a property that whenever you plug in the x coordinate of these data points, you will get the corresponding y coordinate. Okay, so for all of these data points, you should be able to have 1 is equal to P0. And we should have 2 is equal to P1. 92 is equal to P3. And last but not least, 66 is equal to P5. So what is P0, P1, P3, P5? Basically, we are plugging these numbers into the variable x. Okay, basically we are plugging this number into the variable x. Okay, so let's try to plug this number in. So when you plug 0 in, the right hand side should be all 0 because all the other stuff becomes 0. When you plug in 1, you should have R0 plus R1 plus R2 plus R2. Similarly, for 3, you should have R0 plus 3 times R1 plus 9 times R2 and 27 times R2. And last but not least, for 5, you should have R0 1 times R1, 25 times R2, and 125 times R2. So, as you can see, this is a polynomial. These are over here are the coefficients. So in order to determine this polynomial, all we need to do is to find the value of these constant, these coefficients R0 to R3. And here we got a system of linear equation where all the R are the variable. So basically all we need to do now is to solve for this system of linear equation, and we should be able to do that because we learned several techniques to do that already. So here we got four equation with 4 variable, but I already know the value of R0. So I'm going to reduce this system by replacing the value of R0 into these 3 equation over here to make the size of the matrix smaller. Okay, so from here you should have, so all these R0 and now 1. And I'm going to cancel that one both sides. So you should have 1 is equal to R1 plus R2 plus R3. 21 is equal to 3 times R1 plus 9 times R2 plus 27 times R3. And 65 is 5 times R1 plus 25 times R2 plus 125 times R3. So here now we only got 3 equations with 3 variables. You can start using all the techniques that we have learned so far on trying to solve this system of linear equation. Okay, so I am going to use the augmented matrix. You can also try to find the inverse matrix of the coefficient matrix if you want, but here I am into the augmented matrix method. Okay. So here the augmented matrix is 1 1 1 1 1 1 1 1 3 9 37 21 5 what 25 125. Okay. So we are transforming this matrix into its row echelon form. Okay. So as you can see on the second row and the third row, I am going to simplify this row by divide the second row with 3 because you can see 3, 9, 27, and 21, they all have 3 in common. And similarly for the third row, I'm going to divide this row by 5. Okay, so now I have 1 1 1 1 on the first row. On the second row, it should be 1 3 9 7, and for the third row, it should be 1 5 25 and 13. Okay. Next, I am we are transforming this matrix into the row echelon form. So I am going to try to erase all these entries, make them 0. So we are multiplying the first row with -1 and add those to the second and third row. Okay, so 1 1 1 1 0 2 8 6 0 4 24 Okay, next I am going to multiply a second row with -2 and add that to the third row. So we have 1, 1, 1, 1, 0, 2, 8, 6, 0, 0, 8, and 0. So you can do it further by transforming this into the reduced row echelon form, but because it is in the nearly the row echelon form, so I'm going to stop. Okay, so the corresponding system to this augmented matrix over here is R1 plus R2 plus R3 equals 1, 2R2 plus AR3 equals 6, and AR3 equals 0. Right? This is the corresponding system of the new augmented matrix. So as you can see, R3 will be 0. Replace that to the second equation, you got 2R2 is equal to 6, meaning that R2 is equal to 3. So plug in the first row, you should have R1 is -2. So you should have R0 equals to 1, R1 equals to -2, and R2 equals to 3. So that concludes the form of the polynomial Px, which is 1 minus 2x plus 3x squared. And this is the final result. Okay. So I have already explained to you the procedure of how to find the interpolating polynomial correspond to your data. So first of all you need to do is to call out the form of the polynomial based on the number of data you have. So if you have n data, the maximum degree of the polynomial should be n minus 1. So in this case, you will have n coefficients from R0 to Rn minus 1. And because this polynomial, when you are evaluating that at those data points, you will get an equation. So basically, given n data point, you are having n equation with n variables. So by solving that system of linear equation, you should be able to determine the value of the coefficients, which will determine the polynomial itself. And that's ends the process. And furthermore, I have explained why people would care for the polynomial interpolation, because it will represent the relationship between two objects in general case. Okay, so for example, after we have found this polynomial over here, and we want to find the relationship between these two objects. For example, at the time where the x coordinate is 2, for example, all we need to do is to evaluate the value of the final p at the time 2. Okay, so for example, if I plug 2 in, you should have 1 minus 4 plus 3 multiply 4, and this is equal to 9. So this polynomial, it suggests that at the time where x is 2, the y coordinate should be somewhere near 9. Suggest something like that. That's how the polynomial interpolation works. Okay. Yeah, so actually this is all for today. This is the end of this lecture. Do you have any question? Okay. Thanks for listening.